Okay, good evening friends. So we are commencing the new topic from today. Well, that is, as I told you, semiconductor physics. Right? Okay, fine. So I have quickly jotted down some points. I think all of you can read that, but don't read it when I am teaching. Okay, right. So I think you have a glimpse of what is written here. So to begin with, let's define what is electronics, right? So as you can read here, it is a branch of physics as well as electrical engineering that deals with the emission, behavior and effects of electron using electronic devices. Now let me explain this to you. See, now very carefully listen to me. We know what are electrons. Well, in chemistry we have seen what is the role of electrons, and in physics, in conductors that we have studied, we have seen the role of electrons. So in conductors, because of the electric field in the conductor, the electrons are in motion, and the motion of the electron we have conceptualized it as drift velocity, right? So we have studied that theory in detail. So in conductors, the free electrons are moving, they are in motion, and we have what is called as drift velocity, or what we call it as drift current, right? Now here you see we are going to talk about the motion of electrons in vacuum. Okay, motion of electrons in vacuum and semiconductors. Right? Okay. Now again and again I am using the word semiconductors here. So quickly tell me what is semiconductor. Whatever you know, you tell me so that I can elaborate. If you have told what is correct, then I will not elaborate. It's a matter of time. We have got to conserve. Come on, tell me what is semiconductor fast.
Yes, sir. Semiconductors are materials in which, on increasing the temperature, their conductivity increases. The resistivity is higher than that of metals, lower than that of insulators.
Good. Enough. That is important. Okay. So semiconductors are special materials where with temperature the conductivity increases. That's very fine. I would like to add here that it's something called as intrinsic semiconductor. Intrinsic means if you take a substrate, all the atoms in this are that of the semiconductor material, and no other material is there. Okay, no other atoms are there. Okay. Now don't interrupt me. So that is called semiconductor material. Right? Intrinsic semiconductor. Okay. Now one of the important properties of intrinsic semiconductor is that at 0 Kelvin. What did I say? At 0 Kelvin. 0 Kelvin. Okay. You will find that the intrinsic semiconductor material at 0 Kelvin is an absolute insulator. Correct? But as temperature increases, this insulator starts getting, the number of free electrons increases, the concentration of the charge carriers. I repeat, the concentration of the charge carriers keeps on increasing, and thereby the conductivity keeps on increasing. Very well. Okay. So there are lots of wonderful things to be said about semiconductors. At this stage, I would like to tell all of you that we are going to discuss in electronics, the passage of the charge carriers, the electrons in vacuum and semiconductors. That is point number 1. Okay. Then electronics uses active devices. Right? I hope you can see that those words, active devices. Okay. So active devices. Now let me explain this active devices to all of you. Well, now you see, transformer. Okay. I think we have studied transformer in electrical sciences. That is the electromagnetic induction and all those. So you have seen that step-up transformer. Step-up transformer, you give at the primary a small voltage, varying voltage, you will get a higher voltage at the output. And there I told you, the voltage of the secondary is greater than the voltage of the primary, but don't call it as amplification. Don't call it as amplification. And I told you why. Why you should not call it as amplification. It is because there is no power gain. I repeat, there is no power gain. Input power is equal to output power. Okay? Input Vp Ip, output Vs Is is equal to Vs Is. There is no power gain. However, in active devices, okay, what I call it as active devices, okay, so I am just drawing the block diagram. You will learn what is there in this block diagram. So here, if you are feeding the input signal, okay, and you are getting the output signal, okay, of course, you are going to control this. You are going to control this, and I'll tell you that you are going to feed in energy into this. How it is fed and all, I'll explain. Now what you find is that VO can be greater than VI, or VO can be equal to VI, or VO can be less than VI. Nevertheless, but what is most important is PI, that is the power input. And if you are taking the power output here, PO, okay, power input and power output, the power output can be greater than power input, okay, greater than or equal to, right? Now this is possible, okay. Now here you see what happens is whatever is the input signal that you are giving, now the device, what we call it as an active device, it will absorb energy from the external device in such a manner that you will get the replica of the signal at the output, okay, whose energy is greater than input. For example, now when I speak in front of a loudspeaker, I have a mic and a loudspeaker, you know that. So if you see my signal here, it is very, very feeble. Hello, 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 very feeble. But at the other end, it is now in an enlarged format. You hear it very louder. Obviously, I and you can understand that that the input power is very less, but the output power is very large. Of course, if the power, you see that there is an amplifier box. If the power fails, then hello, 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 I will be saying hello, hello. In the loudspeaker, you will not get it hello. So you need an external power source to ensure that whatever input power you are giving, it becomes amplified or it becomes larger at the output. Okay, so there you see we are using a lot of active devices which is responsible for this. Okay, well, that is one thing. Then the other thing that I would like to tell you is, you see, passive effects. Supposing you have used resistor, capacitor, inductor. Okay, now you see, supposing I have a voltage source, right? Voltage source, and I want to control the current. That is, say that there is some device. So into this device, I want to control the current. I want to control the current to this device. So how would I control? Well, everybody knows that you are going to add a resistor here, and if you vary the resistor here, you are able to control the current, because the current IL will be equal to V by R, and if R is variable, this current also becomes variable. Correct, students? Hello? Now, the most important thing is, well, now you see, you have seen rheostat, volume control, etc. You have to physically turn it and all, and then you have these effects. And other thing that we have discussed in electrical sciences is, when you try to control the power like this, there is going to be what is called as power loss. The efficiency of this system is very, very less. We have taken some examples when we have proved. Now, on the other hand, instead of this resistor, we can make use of active devices like transistors and all. We are going to study that. Active devices. There, you see, we can happily control the current or the power or the voltage to the load, power or voltage to the load very, very easily and more effectively and efficiently. Okay, that is possible by the use of active devices and using semiconductors. semiconductor material, you can build active devices. Fine, students, that is important. Now, please try to understand. See, for example, in mechanics, we have studied the fulcrum. That is, you have a long rod, there is a fulcrum, and then you do like this. So, you get, the load is lifted by small power. I think all of you know that. There, we calculate what is called as mechanical advantage. Mechanical advantage is greater than 1. But there you see, the energy there and the energy here are equal. The power there, the power here are equal. There is no power gain. Although you see that there is force amplification, but there is no power amplification. Similarly, when we have studied the Pascal's law, you know that a small boy can lift a car. Pascal law. So again there you see energy here is equal to energy there. Okay.
Yes.
So there is no power gain. I suppose you understood. But now we are going to use active devices and we can get the power gain. That is most important. So what is important now is that we are going to learn the science behind the building of the active devices. Is that clear? Fine. Now, quickly let me tell you, active devices. An active device is any type of circuit component with ability to electrically control electric charge flow. Electrically control electric charge flow. Electricity controlled by electricity. So what I mean is, you have an active device. The input signal that you are giving here is of electrical in nature. The output signal is also electrical in nature, and you are going to use external electric source to control the output depending upon the input. Did you understand this, students? Hello, quickly.
Yes.
Yes. Please, everybody say yes or no. So that is very important. And generating electricity. See, we want energy, right? Generating electricity, transmitting electricity, right? That's how the energy we are getting here. And controlling electricity is very, very easy compared to controlling other types of energies. Okay, that's why you see this electrical sciences become extremely important. Okay, in order for the circuit to properly called electronics, it must contain at least one active device. So if you say there's an electronic circuit, then there must be at least one electronic active device. Active components such as amplifiers, vacuum tube transistors, make use of external power source to add power to the system. Okay, well, I have explained everything here. Okay, if you have any questions here, please ask quickly, whatever I have uttered in that. And if you don't have questions, allow me to move forward. Yeah, please.
Sir, in circuits, we can make circuits as we want, sir, which are functional.
See,
now active components, sir. So, what will those circuits be called?
They are passive circuits. The passive circuits. It only contains passive elements, you call passive. So that is very clear. You will have a lot of passive components, but at least there must be one active component. Then it is called electronic circuit. Otherwise, it becomes electrical circuit. Got it? That's the difference. Yeah. Right. Any other question?
The second point that Pascal's law
Yeah. You see, in Pascal's law, when you have studied the Pascal hydraulic pump.
Yes, sir.
There you see what is that? Here you have got this, and here you have this piston. I suppose you know that.
Yes,
so there is a piston here, and you have another piston here on which there is a platform on which you have got a car. Right? Okay. So here, if you apply, of course, the piston liquid here, right? Liquid. So if you apply Fi here, then you will generate Fo here, and here you see, you know that area and this and all. So you will be able to lift the car by pushing it here. Of course, if you say this area is 10 times this area, if area is 10 times, that is Fi, and the F4 here becomes, if this area is 10 times, then Fi is 1, F4 will be equal to 10 times F4. But the important thing is, if you push this by 10 centimeters, this will go up by 1 centimeter. So work done is same. Okay, 1 into 10 is equal to 10 into 1. Okay, but here you should say that yes, the force is amplified, but energy is not. There is no power gain. That is precisely what I wanted to tell. Okay, fine. Any other questions, students? Well, thank you. Right. So, having said that, we will now get introduced to semiconductors. Okay. Now, the most important thing is, well, you have certain elements such as silicon, germanium, and certain compounds, okay, which have got certain very interesting properties. One of the properties, just as you have, as some of you, as we discussed in the initial stages of this class, that is with the rise in temperature, the conductivity increases. Well, that is fine. But that is not the only important property. There are so many other significant properties of the semiconductors which are responsible for everything that is today. Today I have this electronic board, mobile phone, everything, you know, it's all because of this semiconductor science. Okay, now that's it. Now, importantly, as you have already read few pages and come to this class, you see now if you take the elements such as silicon and germanium, they are having how many valence electrons? 4 valence electrons. Correct? That is common. And the bonding is covalent bonding. Correct? Hello? Hello?
Yes.
Please keep your mic unmuted and please keep telling us no, yes, no. So that's it, and all of you know the structure. I'll be showing you the structure of silicon semiconductor, and so you know all the when I'm talking about semiconductor now, I'm talking about intrinsic semiconductor. Intrinsic means it only contains the atoms of that semiconductor material. For example, silicon. Okay. Now, as you know, at 0 Kelvin, okay, all the valence electrons are tightly bound to its neighboring atoms. Hello, everybody, clear? You have that mental picture? Yes. Now, supposing the external energy is supplied, external assumed thermal energy is supplied, and the bond breaks. The bond breaks. So, when the bond breaks, what happens? The electron from the electrons which are bonded now will become loosened. They will not be bound electrons. Correct? Hello?
Yes.
Yes, what happened?
Most of the respective atoms not.
Pardon?
They'll be with the respective atoms not.
They come out of the bond. They come out of the bond when some energy is supplied, but they are still belonging to the parent atom.
Yes.
Okay, because you are supplied small energy. That is stage 1. That is stage 1. So I said, I have written here, see, energy supplied, the bond has broken. That means the electron from the bond has been loosened. Like we will not say it is bound electron now, it is an unbound electron. Unbound electron. But electron still is near the atom. I hope you can read that.
Yes, sir.
Now, if you supply more energy to unbonded electrons, what happens? These electrons, if these loose electrons absorb energy, then these unbonded electrons will become free electrons. Right?
Yes, sir.
Now, what is a free electron?
A free electron is the one which is not under the influence of any other atoms, and it can move if there is any electric field applied.
Good, fine. But here you see, if you want to precisely define what is free electron, if
an electron situated in the conduction.
No, don't go so far. Don't go so far. See, conduction. See, that's what I'm trying to tell. See, in metals also we have got free electrons. In metals also we have got free electrons, correct? So there you see, how did we define free electron? Those electrons which under the influence of small external electric field readily moves. Such electrons are called free electrons. Got it?
Yes, sir.
That is important. That's important. See, these definitions carry lots and lots of weightage, because if you absorb this definition properly, then you can understand the usage of these concepts and you can learn physics correctly and properly. Right. So therefore, they will become free electrons. Free to move through the substrate. Free to move anywhere through the substrate. As if, it just can move anywhere. Free. Okay, and they are called free electrons. Okay, and now in semiconductors, see, there is the way the electrons are, the way the electrons behave in semiconductors is different from the way the electrons behave in other types of materials, such as the metals or simple conductors and insulators. Right? So the way the electron behaves, we can classify them as conductors, semiconductors and insulators. Okay. So for that, we develop a theory called as band theory. We develop a theory called band theory. Okay. We'll go into that band theory. Okay, friends. Any sentence, any word that you did not understand, whatever I explained now here? Right. I'm just giving you a brief introduction because time is very, very precious for you and me, right? I can enjoy telling you a lot of things here, but I have got to restrict myself.
So what do you mean by substrate, sir?
Substrate means you take a piece of the material. A piece of the material, okay? Just this piece of the material. Okay, this is called substrate. Just one piece of material called substrate, right? That's it. Now, energy bands in solids. Now, here you see there is a theory that is developed. This is called as band theory. Right. As you can see, based on Pauli's exclusion principle, in an isolated atom, electrons present in energy level, but in solid atom it is not isolated. There is interaction among others. Due to this, energy is contributing to energy. Order of the energy bands is so and so. Okay. Now, I think you have briefly read what is written here, right? Let me explain that to all of you. Okay. Now, you see, as it has been pointed out here, isolated atom. So, whatever Pauli's exclusion principle, etc., we have studied. Okay, Heisenberg's principle, Pauli's exclusion principle, to understand the electronic structure, it is based on certain laws like theories given by Pauli, etc. And as you know, Pauli's exclusion principle, no two electrons will have all the 4 quantum numbers same. Correct?
Yes, sir.
So, in one atom, so many electrons are there, each will be distinct. Distinct means because the 4 quantum numbers will be different for each. There will be unique set of quantum numbers assigned to each and every electron. But now, you see, when you take a material, right? Now, what is there in this? This also contains, assume that this is element, This also contains the atoms, correct? But you can see, the atoms are not isolated. They are very, very closely packed. They are extremely closely packed, right? You appreciate that. Okay. Now, what happens? When the atoms come very close, right? Now, what will be the quantum numbers assigned to each of the electrons? In each atom, its quantum number is so and so. But now, since they have come very close to one another, every atom has influence on every other atom. Every electron is affected by almost many atoms around it. Hello, are you with me?
Yes.
In an isolated atom, the energy levels are because of the interaction of the electrons, mainly with the nucleus and also with the neighboring electrons. That's how the energies are specified in isolated atom. Now, the same set of electrons in the atom are not only under the influence of the nucleus of the parent atom, but is also under the influence of the neighboring atoms, nucleus of the neighboring atoms, and also the electron cluster of the neighboring atoms. So therefore, this as physicists, we should be able to appreciate that the energy levels of the individual electron, energy levels of the electrons of every atom is now not simply governed by the Pauli's law of isolated atom, but there must be some other law to establish the energy levels of the electrons. Okay? So therefore, here what the scientists gave a theory, wonderful theory, it is proved beyond doubt. Okay? What they said, well, these electrons, assume that there are so many electrons. Now, for example, if you take silicon, okay, so it has got 4 valence electrons, right? So what are these 4 valence electrons? Silicon has got atomic number 14, isn't it? 14. So 8 in the first shell, right? Then the remaining 6 will be in the next shell, correct? Hello?
Yes.
Correct now? So you will have 2 S2 and 2 P2 in the second shell. And these form the valence electrons, correct? Correct, I'm asking you. Come on. Hello? Okay, see, I had written here deliberately wrong, so that I wanted you to be alert. Thanks for correcting. So, this is the valence electrons. And if there are n number of electrons, n number of atoms in this substrate, then the number of S levels will be so and so. Number of P levels will be n into so and so. Simple mathematics. Okay. Now, what the theory says is, all these S levels and P levels, they will combine. First, they will all combine. Okay. And then the energy levels are established. See, if you have taken individual atom, then you see there are 2 energy levels here. One main energy level, 2 sublevels, orbitals. Here, one main energy level, 2 sublevels, and 6 sublevels. Main, 2 sublevels, main, 2. Here, there will be 3 P6. So, of 3 P6, 2 of them are occupied. Remaining 4 are vacant. I suppose all of you know that. So, you know how the energy levels are there in isolated atoms. Now, in isolated atoms, you can show the energy levels like this. You can show the energy levels like this in isolated atoms. You can assign it to this. I suppose you understood this. Hello?
Yes, sir.
This is how the energy levels are there in isolated atoms. Now, what is done? This n into this is multiplied, and then our mathematics would have said, sir, these are like this. So you simply multiply it and make it n times more. That is what I and you would have, simply written it up. Correct? Hello? But there is an important difference. What happens in semiconductor is slightly interesting. Okay? Now, here you see the spread is not simply like in an isolated atom. In an isolated atom, you have the spread, but in a substrate, that is in a material like this, where there are millions of atoms, the spread will not simply be like this. The format of the spread will not be simply like this. It will be slightly different and very, very interesting. Did you appreciate what I said?
Yes, sir.
Now, what I said here was something like this. Okay, what I said here was, now they will form 2 sets of energy. Okay, now that means now n into this, it will form energy levels, but there is a gap here called as forbidden gap. Now try to understand the meaning. Very simple. The electrons can occupy these energy levels. One energy level per electron. Okay, or these energy levels. Right. Now, what do you mean by energy level here? The electron will have this energy, or this energy, or this energy, or this energy. But it cannot have any energies in between. Got it? Even in an atom, either it will be in first orbit or second orbit. In first orbit, this orbital, that orbital. In between, it cannot have any other energy levels. It is discrete energy levels. Got it? They are not continuous energy levels.
Yes.
So same way, you have this. You have this. Now, the interesting part is, at 0 Kelvin, intrinsic semiconductor. Say, for example, silicon. All the valence electrons will be in this band of energy levels. All the valence electrons will be in this band of energy levels. Okay, and there is another band of energy levels after this forbidden gap. Forbidden means there are no energy levels here. That is why we call it as forbidden gap. But what you find is these energy levels called as conduction band. Conduction band. Band means many energy levels. And this, since we will find only the valence electrons here, this we call it as valence band. Okay, what is valence band? You see, silicon has got valence electrons, so they are in the covalent bonds, and these valence electrons you will find it in these energy levels, and there is another band of energy levels which is empty. Okay, and there is a forbidden gap. So this is at 0 Kelvin. Fine. Did you understand this?
Sir, those energy levels are the energies of those orbitals.
Correct. But these orbitals now are not the same as the orbitals of the individual atoms. They are different now.
Sir, they will be like that because their energy will either increase or decrease.
No. Let's not go about increase, decrease, and all that thing. Unnecessarily, let's not complicate it. I just want you to appreciate that the energy levels of the electrons which it had occupied in the isolated atom is now different.
Okay, sir.
Hello, are you all with me?
Sir, different in what respect?
Different in what respect? Now you see formerly each atom had a set of energy levels. Correct? Now these energy levels have all combined and they have formed a new set of energy levels, which is different from the energy levels, designated energy levels that were there in the isolated atom. That's all. Now don't attach any more strings to that. See, for example, in an atom, supposing you have taken one particular atom and you said it is 3s1. So 3s1 in an isolated atom would have got some energy, correct?
Yes, sir.
Now the same atom, this very atom, when it is a part of this system, will not be having this energy. It will be having some other energy. Got it?
Yes, sir.
That is what I want to tell you.
Sir, that atom will have some other energy, sir. It should be similar with all other atoms.
Similar with the see. That's what I'm telling. It cannot be similar. That's a nice question that you asked. It will not be similar. Why? Because now you see the electronic system of atoms. Electronic system of a single atom, electronic system of a system of atoms. देखो, तुम अपने घर में, in your home, how are you? You are the way you are, correct? Now supposing you go to a picnic. You go, all your friends, all of you go to a picnic. So you are all now in one room or one hotel or somewhere. Now, will you occupy the same position, same comfort as you were in your home? Definitely not.
No.
You are still an individual, but now you know how you have to behave will be different. because you are under the influence of your friends, your space around you. So what has happened now? See, now when you go to a picnic, you are from different homes. Say there are 100 students, 100 homes. In your home, you are king, right? Okay. Now every student is a king in his home. But now all of you go to a picnic. Now what happens? All of you have joined. Now your teacher will assign. Okay, you sit here, you sit here, you go there, you go there. In your home dining table, you would have got a chair. Okay, this is my chair. Always I will sit here. Now everybody has that, that front chair, main chair. But now when you are in a group, you cannot say I will sit. So in my home I was sitting here, I will sit here only. Then that fellow will also tell. So what will the captain do? He will allocate different chairs and he will say all of you sit in different chairs. Order has changed. Same thing happens here. Got it?
Yes, sir.
Understood?
So those conduction bands are also because of some atoms.
See, now energy levels means like this. Now assume like this. Say, supposing now you go to a classroom. You go to a classroom. So now there are 100 benches in your classroom. And say there are now 40 students in the classroom. The teacher will tell you, you sit here. Adil, you sit here. Abhirav, you sit here. You sit here. He will allocate the places and you will simply go and sit there.
Yes, sir.
So there are 100 benches in the class, right? But there are 40 students. So 40 benches, first 40 benches, the teacher will allocate to all of you. Now these 40 benches, I will call it as valence energy levels. There are remaining 60 benches, which are empty. But your teacher can tell, hey, you go and sit there. So there are empty energy levels which can be occupied by the electrons, but which at the present condition it is not occupied. Is it clear?
Sir, according to what they have written there, sir, in the note, can we put it this way, sir? Now that there are many atoms and there will be interactions between them, either repulsive or attractive.
Why you want to go to all those things, man? Why you do want to read all the things now? I am trying to avoid all those things. Why do you want to create that theory? No, I am explaining something. Focus on this, Mr. Avi. Now, don't try to create some theory here now. It is already done. It is interacted. That is why these energy levels are there. Why do you want to put that thought again? Now, just understand the statements I am doing. In that, if you have any doubt, you ask. Now, you don't bring another theory here. That is not the way to learn. It is a huge science. I have got a book on semiconductor physics here. It is 1000 pages. Understand? I can't teach you 1000 pages here. Okay, for your PUC level, what is necessary, that much only I will teach you. Is that clear?
Yes.
Please, in what I have said, if you have doubt only, you ask. Now, don't bring any other theory in between. Please. Okay, so you have 100 students. Wait a minute. This boy distracted. There are now 100 benches. You are 40. The teacher has allocated 40 seats to each one of you. Okay, so these 40, say, supposing he designates 45 seats, and in those 45 seats, he has asked 40 students to sit. These 45 seats are called valence energy levels or valence bands. There are another 55 seats at the back which are vacant. But they are also energy levels, which I am going to call it as energy levels in the conduction band. Is this theory clear?
Yes.
Okay. Mr. Arun, ask your doubt.
Sir, this conduction band, sir. The energy levels, like it is continuous band or distinct?
Discrete. See, I have written here. No, when I write like this, it is discrete. All these energy levels are discrete. And they have a small energy difference between them, very small. Okay? For all practical purpose, you can say it is negligible and they are discrete. Okay, fine. Any other question? No questions? Good. So therefore now, at 0 Kelvin, intrinsic semiconductor, all the valence electrons, are bonded to the neighboring atoms and they have occupied any of these energy levels in the valence band. Clear?
Yes, sir.
And there are no electrons in the conduction band. That is the condition at 0. Clear?
Yes, sir.
Now, suppose now you consider this electron. Okay, this electron is very close to this energy level. This electron is very close to this energy level. Okay, now and this is all these electrons are bounded, covalent bonded to a neighboring. Now, supposing this electron is given some energy and the bond is broken. What did I say? The bond is broken. What happens to this electron? If you have read, pardon?
It will get excited.
It will get excited. Where will it be?
If it gains sufficient energy.
So I have just given energy to break the bond. So it will be anywhere here only. Got it?
Yes, it will have free electron.
It has not become a free electron. It has not yet become a free electron.
Yes, sir.
It is still a part of this band. Or for example, say this electron is broken. So maximum this electron can go here, provided this is empty. See, this energy level cannot occupy 2 electrons. It can occupy only 1 electron. Supposing this was vacant, this energy level was vacant, okay, and there was an electron here. It got some energy, it broke the bond, and slightly more energy it might come here, right, or here. But still, it is a part of valence band. Got it?
And here, initially, I just broke the bond.
Just broke the bond.
Okay, yes, sir.
Just broke the bond, and slightly more energy if you give, somewhere here it will be. Got it?
Yes, sir.
Now,
Which bond are being seen?
one of the bonds.
That means which one?
Which one means?
That whole.
Which bond? See, each electron is bounded to the neighboring atom. I think you have studied and come to the class. With that presumption, I am teaching.
Yes,
This diagram, man.
yes, sir.
So, each silicon atom is bonded to its neighbor. Hello, this bond has broken. So that means this electron has come out of the bond.
Okay.
But it is just come out of the bond. That means it is somewhere here only. Got it?
Yes, sir.
That's what I want to tell. Is it clear?
Yes, sir.
Now, supposing you give some more energy to that. Some more energy to that. Okay, that means this electron has broken and it has come here. Now, if you give some more energy to this, what will happen to that electron?
Sir, depends.
Continue.
If you
On
give
the
some-
capital gap, you can't.
If I give energy greater than this level, that is, the energy I give to this electron must be greater than this difference, forbidden energy level. Then this electron will come here. Got it?
Yes.
Yes, sir.
Otherwise it will not. Otherwise it will not. Otherwise it will not. It will still continue to stay there only. Okay?
Sir, one more. Sir, here, sir, you are supplying energy, sir. So the bond will break. After you supply some more energy, sir, other bonds might also break.
Other bonds also can also. Very good, very good. So that is why it is a probabilistic theory. It is a probabilistic theory. Other bonds can break, and some electron which has come out of this bond can go and enter into another bond.
That whole
कुछ भी हो सकता है. हाँ, सभी bonds will not break at the same time. It is a probability. Which bond will break, that the theory cannot predict. Only probability for this energy, so many bonds will break. Which exactly bond will break, that we cannot say. Okay, got clarified? Yes, please. Good. Okay, so now I think it is very clear that some energy is given, bonds are broken, slightly more energy, they might travel from lower to higher energy level, but if it gets sufficient energy greater than this forbidden graph, then only it will jump to the higher energy. Clear?
Yes.
Yes, sir.
Now such process carries on, and if you find electrons in this band, then these electrons are called conduction band electrons or free electrons. Right? So now you see, they are discrete in nature. Order of the energy levels in the band is 10 to the power of 23, and their energy difference is after the order of 10 to the power of minus 22 electron volts. That is in the case of isolated atom. Right. Now, range of energy possessed by an electron in solid is known as energy. Range of energy levels. I have shown you like this. Range of energies possessed by valence electron is known as wavelengths. Have bonded electrons, no flow of electrons due to such, always fulfilled by electrons. That is valence band. Got it? Conduction band. Range of energies possessed by free electron on conduction band. It has conducting electrons. I have explained what are conducting electrons. Current flows due to such electrons. If conduction band is fully empty, then current conduction is not possible. It is a perfect insulator. Electrons may or may not exist in this. So in an intrinsic conductor, semiconductor at 0 Kelvin, there are absolutely no conduction band electrons. As temperature increases, it increases. Got it?
Always fulfilled by electron.
Yes. So that means now what they have missed out is at 0 Kelvin intrinsic semiconductor, the valence band all the valence band will contain the valence electrons.
Okay.
That's right, that word is missing there. See, that's what I am trying to tell you. In textbooks and all, see, if you want to really learn this, you have to read hundreds of pages. I've got books here. There is no time for all of you. So I have abstracted things from that, taken as points, and I am elaborating it here very clearly, open for discussion. That's how learning should take place, not simply reading and writing. Clear?
Yes, sir.
Now, some thought about forbidden energy gap, delta Eg. So delta is yes, please.
Sir, insulator can also have a conduction.
Insulator. Yes. Insulator can also.
Yes, sir.
Insulator can also. Okay. Now,
Yes.
since CNC, I have asked a question. See, now if you, let me just to say. Okay. See, now silicon, okay, germanium, okay, and such other things. They are all tetravalent. Carbon is also tetravalent, correct? Carbon is also tetravalent, but carbon is not a semiconductor. These two are semiconductors. Okay? Why it is not a semiconductor? Because in carbon also there will be energy levels. Okay? Valence band and conduction band. But this gap is so large. That the valence band electrons, okay, cannot jump to this under ordinary circumstances. Understand? So therefore, the carbon remains as all the electrons in the carbon remain in the valence band. Got it?
One question, sir.
Wait a minute. See, you have got a bad habit. I was explaining Mr. Arun. Let me complete. Let him say yes, then you can ask. Did you get it, Mr. Arun?
Yes, sir.
On the other hand, if you take metals, there are energy levels. Okay, there are energy levels. Valence band. Interestingly, the conduction band will also see these yellow lines are conduction band. You can see that the conduction band energy levels and the valence band are overlapping. That means an electron here is both a valence electron as well as it is a free electron. This is possible in some metals. Okay, that is why even at ordinary temperature, metals are good conductors.
Yes, sir.
That is, so even in metals you have got energy band theory, in insulators also you have got it, and in semiconductors also you have got it. The most important thing is in semiconductors, this forbidden gap has got very, very small value. Right? And because of that, you are seeing all this chamatkar, mobile phone, television, etc. We will understand that. Mr. Abhinav, you had some doubt.
So you had said that carbon, that forbidden energy gap is very high, sir. Then why graphite and allotrope of carbon can conduct electricity so well?
Why it can conduct
electricity so well, sir?
Electricity so well. Graphite.
Yes, sir.
Okay. See, now what I said here was that, if there are valence electrons here, this cannot easily jump. But if there are electrons in the conduction band, they will be there. See, this jumping phenomenon will not take place in the carbon or its allotropes. Is it clear?
So, but carbon itself is an insulator.
No. Listen. That's what. See, the molecular structure of that is different. So, the energy band structure there will be different. Understand? I am just showing a schematic of that. But now, no confusion whatsoever. There are energy bands, valence and conduction bands in all these things. Either they are overlapping or the difference is very large or small. That's it. Every material will belong to one of these three categories. Got it? So, it is the structure, the molecular structure, which will give it all its properties, including its color, conductivity, shine, density. Everything is decided by the molecular structure. And you being students of chemistry, you know that much better than me. Clear?
Yes, sir.
Okay. Now, forbidden energy gap. Okay, that is delta Eg. Now listen here. CV minimum, VB maximum. That means what? That means CV minimum. This is CV minimum. Okay, and this is VB maximum. So this difference is called the forbidden energy gap. Energy gap between conduction band and valence bands where no free electron can exist. Width of the forbidden gap depends upon the nature of the substance. Width is more, the valence electrons are strongly attached to the nucleus. Width of the forbidden gap is represented in electron volts. As the temperature increases, the forbidden gap decreases very slightly. So, this forbidden gap will decrease slightly if the temperature increases. This can be a very important question in your examination. Okay?
Sir, one doubt, sir. Why can't any electron exist in the forbidden gap?
See, these questions you should avoid, gentlemen. You should avoid. See, you have studied so much of chemistry. What is that you have studied in chemistry? They are very clearly specified that electron cannot occupy any energy level. They can only occupy discrete energy levels, even in the isolated atom. That is why you have got the 4 quantum numbers. Correct now?
Yes, sir.
Then why are you asking that question? See, that is.
But now we are no longer.
That is why. See, that is why the starting statement was Pauling exclusion principle is also applicable for this material, but in a different way. Understood? It's in a different way. It will not be continuous at all. So it is discrete. And that is precisely what I have been telling, many times. Discrete. That is the beauty of science. Right? That's the beauty. They built the theory, they tested the theory, they experimented, and they got the results as expected. So the hypothesis after due experimentation has got converted to theory. Once it is a theory, we have accepted it. We simply have to use it and apply. We should not once again start reinventing the wheel. Is that clear? Right. Okay.
Yes.
Shall I move on, students?
Yes, sir.
Yes, sir.
Right. So here we go. Now classification of conductors, insulators, semiconductors. On the basis of relative values of electric conductivity, energy bands, the solids are broadly classified as conductors, semiconductors, insulators. Okay. So I will state the properties. You can read it. Resistivity of conductor, very small, right? Semiconductor, insulator, conductivity opposite of that, temperature coefficient of conductor positive, temperature conductive of semiconductor is negative. What means what? See, if the temperature of a conductor increases, its resistance will increase. For a semiconductor, if temperature increases, what happens? The resistivity will decrease, or the conductivity will increase. Very important. And for insulator, it is negative, very slightly it is negative. Okay. Current. In a conductor, it is due to free electrons. In semiconductor, it is due to holes and electrons. In insulators, there are no conductors. Now, I will explain the concept of holes to all. Right? I think you have heard about holes in the textbook.
In chemistry, we had this.
Tell me, what are holes in semiconductors?
Sir, if we consider the crystal structure, sir, as you have drawn earlier, you please draw to silicons.
Silicons.
Yes, sir. Silicon or any semiconductor.
No, that's not it. That's not. Maybe you are telling right, but that is not the appropriate answer. Anybody else? What are holes? Come on. No, don't guess and answer. I want precise definition. Precise. Not beating around the bush.
The absence of an electron from its position where it is supposed to be in the valence band, sir, is a hole, sir.
Good. That I agree. So, you see, you should have told me, sir, draw conduction band, forbidden gap, then draw valence band. You should have told me this. I agree with you.
Actually, in that bond.
You should tell here, you should use the bond structure. Connection. Okay, now, say there are electrons here. Right? Say. Now, you see, this electron gets some energy, and if it gets energy, this electron will leave this place and it will go here. Okay? Now, you see, this energy level, okay, you can see here, earlier there was electron here, now there is no electron here. So, what I will say here, the empty energy level in the valence band, which hitherto was occupied by a valence electron, is now empty. What did I say? An energy level in the valence band, which hitherto was occupied by a valence electron, is now empty. This energy level is called hole. Did you capture what I said?
Yes, sir.
Now you see, there is an energy level which is empty here in the valence band. Do you call this as a hole?
No, sir.
Because it was not earlier occupied by a valence electron. Correct? Right. So therefore, and one more thing. Say, supposing now there is an electron here, and now what has happened? This electron, now there was an electron here. Now this electron leaves and comes to this place. Now the empty space created here is also a hole. It necessarily doesn't mean that electron should leave here and go here only, then hole is created. So holes are created within this also. Okay, within this. But if a hole is created here and usually what happens, a hole is created here, the electron will come to the conduction band. So what I am trying to tell you is, for every electron added to the conduction band, there has to be a hole in the valence band. Got it? For every electron present in the conduction band, there must be a hole in the valence band. Did you digest this statement?
Yes, sir.
Yes.
Come on, everybody there, confidently say. If you have a doubt, you ask, I will explain. For every electron created in the conduction band, there must be a hole in the valence band.
So we are considering here intrinsic semiconductor.
Yes, only intrinsic. I am only talking intrinsic semiconductor.
Okay, sir.
Clear?
Yes, sir.
Yes, sir.
Now, this electron and hole. So you have got electron and hole. Okay. Now, under what are these two? What are these? What are electrons and holes?
Charge carriers.
Excellent. They are charge carriers. Excellent. Charge carriers. That's important. See, you have got ions in the solution. Ions are also charge carriers. Correct? Ions are also charge carriers. Electron will carry negative charge. Hole will carry positive charge.
So one doubt has.
Please.
Respect to holes. Like, sir, as when you say ions, like there will be proper protons that will be responsible for the positive charge, positively charged particles. But hole we are defining on the basis of that electron should have been there, but it is absent. So how can we say that it is carrying a charge when it is actually the absence of a negative charge that is?
I have not yet completed anything more about holes. I only see whatever I have taught, that part if you have not understood, you ask question, gentlemen. See, I know you have read something more and come. Don't distract. I have not yet completed that. I was just introducing that. I just said what are holes. I have not yet spoken anything more than that. I was just telling you they are charge carriers. Electrons carry negative charge, holes carry positive charge. Okay, that's it. To that extent, if you have doubt, you ask.
Yes.
Done. Okay. So now you see, all of us know that if you have an electron and this electron moves, right, then the conventional current is opposite to this. Correct?
Yes, sir. Yes, sir.
Now you see, there was an electron here in this position, and now what happened? This electron from position P1, it has moved to position P2. So since it has moved to position P2, what happened? Here a hole is created. Correct? Here a hole is created. Here in position P1, a hole is created. Agreed?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Now please try to understand this very carefully. The electron was here, the electron has moved from here to here. So the conventional current is in this direction. Correct? So this keeps on moving, assume that the conventional current is in this direction. Now try to understand. Now here you see there is one more electron. There is one more electron. Okay? Now you know there are bonds. I think all of you know the silicon structure. There are bonds. Now for some reason this electron which was bound to its neighbor has loosened. Then what happens? This electron can go and fall into this hole because this is a process. This electron will go and fall into this hole. Why? Because this is an energy level which can hold the electron, and this energy level is now empty. So there is provision for the electron to go there. For example, in your classroom, your teacher allocated some seats. You sit here, you sit here, you sit here. For some reason, one of the friends moved from that seat and moved to some other seat. That seat is vacant. So somebody can go and occupy that seat. Correct? Because it is vacant. Hello?
Yes.
Same thing. So because this is vacant, this electron can go here. Correct?
So, but what will drive it?
I will explain it. See, this electron was driven by some force, say external electric field, temperature, whatever it is, this electron was propelled from this point to this point, and therefore the current is in this direction. Now that there was a hole created here, and this electron here, for some reason, just loosened out, And since there was a hole here, there is a possibility and say not possibility, this electron, because there was a hole here, this electron jumped from here to here. Got it?
Yes.
See, I will explain under what mechanism it happens. We will discuss that later. But there is a provision. See, in your college, one seat was there, a prominent seat. Now that student who was there, he has gone out or something. So somebody can go and sit there. Correct?
Yes.
Why did that fellow go and sit there? There are many reasons. Correct? No.
Okay.
Adil, you would have also done this. You would have gone and sat in that seat, prominent seat.
Yes.
For what reason? There are many reasons. Correct? No? There are many reasons. Yeah. College students, you have many reasons to change the seats. Right. So that has happened. Now, अभी क्या देखना है कि an electron from here has gone here. Now what happened here? This energy level now becomes a hole, and electron comes here. Correct? So here you see, here in this case, the hole has moved from here to here. Electron has moved from here to here. Correct? But at the same time, the hole has moved from here to here. Appreciate it?
Yes.
Now here you see the measurements that are carried out here. Very interesting measurement. See, in a resistor, if an electron from here has gone to here, okay, you can measure this current. Now, an electron has gone from here to here, and if you measure the current, now please be clear here. So, if you measure the current, this current will not, see, now I call this as electron current. Now, here in this case, the current that you measure here will just not be electron current, but this will be more than the electron current. The magnitude of the current is not simply IE, but it is more than IE. How did that more than IE come? Scientists investigated and they have come out with this whole theory. Right? And that means now when this has happened, when I explain this, there are two currents that are flowing. One is the electron current and other one is the hole current. This happens only in semiconductors, not in metals and other conductors. And therefore, this hole becomes one of the predominant charge carriers in a semiconductor material. So therefore, in semiconductors, you have two types of charge carriers, one electrons and one holes. Electrons carry negative charge, holes carry positive charge. Because the direction of current is enhanced. The magnitude of current is enhanced in the same direction. Is that clear? Please ask.
Those concepts of drift velocity and conductivity.
Pardon? Once again?
The concept of drift velocity and other things can't be applied.
We'll come to that point. Yes. Okay. So here also you see this current what I have shown here, is definitely the drift current only. Same like how we have studied in metals, same way. Yes, these electrons can also go and bombard, collide. Holes can go and collide. Just like how electron. Pardon?
The holes are those empty spaces.
No. Listen carefully. See, listen carefully. See, at every stage, you have to absorb and, you have to now understand it like that and proceed. What I mean is, I have defined the empty energy levels hitherto occupied by valence electrons as holes. Okay, got it? That is one stage. Now you see, you should start looking at holes. You should start looking like holes as if they are particles similar to electrons. Listen, now in the science that we are studying, in one point we will say electron is a particle. Somewhere we will say electron is not a particle. I suppose you will understand it better in the higher classes. So see, light we have studied. Light, is it consisting of particles or is it a wave? We have already studied dual nature of light. We have accepted that.
Yes.
Correct? Okay. Same way here we have to accept. Okay. Now, if you say electron is a particle, then this is best understood. This explanation of this is best understood if you can consider electron as a particle. Okay. Now, you now also consider hole as a particle. What is your problem? No problem. See, these are concepts, man. किसने देखा इलेक्ट्रॉन को, किसने देखा होल को, किसी ने देखा, किसी ने एटम को देखा, नहीं देखा. लेकिन we have created that concept, just like how we have created the concept of, the Almighty. Yeah, see, if you believe there is God, there is God. If you don't believe there is God, there is no God. It's the belief system. Got it, all of you? Hello?
Yes, yes.
It's a belief system. Okay. See, because we are human beings. See, we have to create. See, if you say, well, there is a system, and if you start believing in that and then start going in that direction, then you will see many things. Now you see, our belief system that there is the smallest individual particle which has all the properties of the element, we call it as atom. Nobody has seen atom. So we believe that atom is like that. Then we have believed the electronic structure. We have believed so many things. And we are seeing the reality. You go to the laboratory and you have conducted so many experiments. All of them, all the results are whatever you had expected so far. So the concepts are now being accepted because experimentally they are proved. And many things around you are realities today. It's all because you believed atom is like that. Same way, my dear student, you have to believe that whole is also a particle-like thing. Now, just like an electron, whole is also a particle. Only thing is that electron has got plus charge. The electron will have minus charge, hole will have plus charge. And there is a mass of the electron and there is mass of a hole. Now I am sure you are going to ask a lot of questions. Okay, now please understand. What is mass? What is mass? If you understand what is mass, then you will have no difficulty in understanding this.
It is a measure of inertia.
Yes, that's it. So therefore, hole has got more inertia than electron. Experiments have proved it. Okay, so they have established this, and we have established mu mobility. You remember? So we used to write here V is equal to mu V, mobility factor. So now here you have mobility of hole is different, mobility of electron is different. So all this is established. So at this stage, you have to understand it like this. In a semiconductor, there are two types of charge carriers, holes and electrons. Holes are positively charged, carry positive charges, electrons carry negative charges. That's it. Okay, fine. Now you see there are holes and there are electrons. So this is electron and this is hole. So if the electric field is in this direction, external electric field is in this direction, what happens? In which direction will the electron move?
Opposite.
Yes, electron will move in this direction. In which direction will the hole move? It will move in this direction. But hole is positively charged, electron is negatively charged. So what is the direction of current due to electron? Like this. What is the direction of current due to the hole? Like this. So this is electron current and this is hole current. So they carry. So every motion of an electron means it has created a gap, and that means holes are moving in opposite direction if electrons are moving in this direction. And therefore the current will be this plus this. I am talking about an intrinsic semiconductor.
Wonder, sir.
Yes, please.
Sir, electrons will move in the direction of electric in opposite to the direction of electric field after they have reached the conduction band.
Yes. 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 So wait a minute. Let me capture your question. Please ask your question once again.
Well, the electrons will move like to opposite to the direction of electric field only when they are free, no sir.
Wait a minute. Now, when I was explaining this theory here, okay. Now, please understand this theory very carefully. See, when I was explaining this one here, this was all happening within the valence band only. Wait a minute. It was happening within the valence band. Point number one. Point number two. See, if an electron jumps from the valence band to the conduction band. Hello. See, now you should get a clear picture. You should know, because I am drawing the energy levels like this. वो ऊपर जा रहे, वो नीचे आ रहे, ऐसे नहीं. अभी इसमें energy levels का ऊपर नीचे नहीं रहता. वो only on the board I am showing ऊपर नीचे.
Yes.
So there are energy levels everywhere here.
Yes.
So they move. So an electron from valence band, if it goes to conduction band, okay, that means what? A hole is created in the valence band and electron is in the conduction band. So it has moved from one point to another point, P1 to P2.
Okay.
Correct? Right?
So like in the direction of electric, opposite to the direction of electric field, sir. That how like in the valence band itself.
Now let's see. Now that's right. Now if I show there's an electric field here in this direction. Now when I'm showing you the electric field and all, now forget that band structure. Now you have got now holes and electrons. They are particles. ये दिमाग में लगा के you start learning. Now see that energy level is over now. Now you should start seeing the holes and electrons as particles. And now if you apply electric field, what happens? See, my dear friend, yes, your question is quite pertaining. To answer your question, I should give you the mathematical model of the energy band system. What you are seeing now here is just an idea about how it is. But in reality, if you see the book on semiconductor, it's a very complex mathematical model. Okay, so now in the complex mathematical model, you will understand. Like for example, in chemistry also, Schrodinger's wave equation, correct? Very complicated equation. Hello?
Yes.
Right? Solution to that gives you what? The 4 quantum numbers associated with each electron. Correct? Now, having accepted that, we are simply writing 1s1, 2s2, like that we are writing. But frankly speaking, how you got that? That's a complex mathematical model. Once you have established the electronic structure, now learning chemistry was easy. Now, every time your teacher is going to say, oh, bond is formed, then you start applying Schrodinger's wave equation, life would have been very complicated. See, the system of the science subject is built in such a manner that at every stage, you consolidate the concepts and create another concept, a consolidated concept, and then you move on. Just like how you created the concept of electron hole using the energy band. Now, forget the energy band. Take now, hole is a particle, electron is a particle, and move on. Now, don't complicate your life by saying that, oh, the band is like this, so it will go up, down. It's not as I showed you here. Tak, 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 band, tak, 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 band. ऐसा नहीं रहता. They are only energy levels. And that is there everywhere here. Is it clear?
Then what is the significance of conduction?
See, the significance of, okay, that is a good question. Significance of conduction band is that electron has now, because of the energy it possessed, has now become a free electron. And we are now putting it in a zone called conduction band. That's it.
That electron can also move opposite to the direction.
That electron can also move
opposite to the direction of electron.
all electrons will move opposite to the direction of electric field, whether it is valence or conduction band. There is no difference. Electron is electron.
So electrons in valence band are also moving, conduction band are also moving.
Let it see. That's what I'm trying to tell. See, within the valence band, if the electron moves, holes are also moving in the opposite direction.
Yes.
In valence band, if the electron moves from this bond to this bond, then the hole will move from this bond to this bond. That also is happening there.
Yes, yes.
This also is happening. It's a very complex process.
No. Yes.
So for us to understand the physics of PUC2, semiconductor physics, we at this stage should now understand that there are two particles, one hole and one electron, right? And treat it accordingly. Now forget the energy band at this stage. Don't complicate it by using energy band. That is precisely how you have to learn science. Okay. Well, any other student has any other question? Okay. Thank you very much. Now what's the time? It's close to okay, close to 9. 1 minute, let me complete this. So energy band diagram, I think I have already explained this. So for a conductor, you can see there is overlap here, no gap. And for a semiconductor, you have got energy band approximately of the order of 1 electron volt. In an insulator, it is greater than or equal to 3 electron volt. Therefore, it is an insulator. Okay. Forbidden energy gap for conductor is 0. So platinum, aluminum, copper. Semiconductor 1 electron volt, germanium, silicon, gallium arsenide, GaF2, and wood, plastic, diamond, mica, greater than this. Some examples. Okay? Done? So I have explained this concept of holes. Right, you can read this. This equation I'll explain tomorrow. This one you observe. Okay, is this points clear to all of you? Now, okay, today only I'll explain this to you, not tomorrow. Okay, fine, because I have explained all those things. So hole acts as a virtual charge carrier. Okay, now there is no physical significance of it. But yes, it has got mass. Its effective mass is more than this, its mobility is less than this. That aspect also I have explained to you. Now, N stands for the number of electrons reaching from VB to CB as temperature T increases. Okay? Now you can very well see at temperature T is equal to 0. Okay, N is equal to 0. So as temperature T increases, you can find that there are many electrons from the valence band which has crossed over to the conduction band. Eg stands for what? The forbidden gap energy level. K Boltzmann constant. A is the constant for a given material. T absolute temperature, gap. In silicon at room temperature, out of 10 to the power of 12 silicon atoms, only 1 electron goes from valence band to conduction band. In germanium at room temperature, 10 to the power of 9 germanium atoms, only 1 electron will go from this to this. Therefore, you can see germanium is more sensitive to temperature than silicon. Rough idea. So most important is N is proportional to P raised to 3 by 2. Okay? Clear, friends? Any questions?
Sir, this will represent number of electrons reaching from valence band to conduction band, sir.
Correct.
And in the process, there will also be one hole created, sir. So can we also like in an intrinsic semiconductor, sir, then this will also be the number of holes that are generated.
Excellent, correct. And the next statement I was going to make it like this. There is something called as mass law relationship. I'll explain that. That will give you the relation between the electrons and holes. Okay, I'll explain that. So obviously, it is obvious. If the electrons have gone with, the whole number of holes are created there.
Yes, sir. Yes.
Okay. Okay. Hello, everyone. Right. Okay.